All right, let's look at the gauges I have already and see why I can't use them for measuring this particular groove or grooves like it. First of all, the groove is almost 7 inches deep in the bore, so that's like this deep. And this would make it, but the tips of these anvils are too wide. They can't go in a groove that small. They're about 65 thousandths or so wide, and the groove is 40 thousandths. So even though this would actually measure the size and everything and the depth, it won't really fit in the groove. Now, a tool like this from Mueller gauge, if you made long anvils, could work possibly, and these particular ones would actually fit in the groove if they were long enough. But this has the thing I don't like too much about these gauges when you get to these longer anvils is they flex, and depending on how much weight you put on your arm, it takes kind of a lot of skill to use this kind of a gauge and get accurate results that way because of the flexing of the gauges. Although this is a very smooth instrument, but it has a lot of spring pressure on it too, quite a bit. So that's not really that great. Now I've made, like here, I made special anvils for this gauge maker thread measuring device, which actually their normal anvils are like this, and they take you put these spherical points on there, and with their software you can check you can set the gauge on gauge blocks. They give you the dimensions, and then you know what pitch diameter you're measuring with the particular diameter spherical ball and everything that they sell. And these work good for measuring threads. I've used this gauge a lot for that. And I use this for measuring the width of a keyway way up inside of a part. And it worked for that all right, but even still, even with the length of these, I need to go this deep. And this here wouldn't make it, even if I put, little anvils on the ends of these arms, and the shape of it's wrong, it would hit the bore and it wouldn't fit in the bore correctly. So I'm left with this gauge, which I designed. I'm going to show in this video how this works, and the thing is, this doesn't have any flex in it because all the measuring's taking point out in the end like a dial bore gauge. But a dial bore gauge, of course, won't go up into a groove. And also, this tool that I'm making here could be used for measuring a shallow counterbore way up in a bore, if you will, that you can't get a dial bore gauge into because of the diameter of the ends of it here. Or even a larger one that has these kind of wheels and stuff, and you can only get so close to the end of the bore with this device. So if you need to get all the way to the end of the bore, I could use this gauge that I've designed here, because I can get, I don't know if you can see that close up to the end of the bore here, where the end of the stylus is, or the anvil. And also there's not tons of pressure on this compared to these gauges. These gauges have awfully strong spring pressures. I've even put this rubber band around here to reduce that in the case of this. And this one has less pressure, and I can open it, or collapse it, I should say, with this little handle I put on here, and get up in there and let it expand out, and then rock it back and forth. So I would have to set this on a set of gauge blocks like a dial bore gauge or any one of these gauges, except for this one. It's kind of calibrated with its dial indicator, but this is a little bit tricky to use if you want to get to real close tolerances, like plus or minus 1/1000th of an inch or so is maybe all I would ever trust this to. It's kind of like a pair of calipers, the accuracy is sort of similar to that, but this can actually be as accurate as a dial bore gauge depending on the indicator you put on it, the way that I've designed this thing and the way it works. So let's get into the video and showing my idea and the design and the thing I modeled to make this and making this gauge. So what you're seeing here is the gauge in the part that I more or less designed this gauge to be able to measure. I didn't have a way to measure this hole or this groove back up in the bore. So let me cut a section through the part here. And you can see a section through the gauge as well. And this ring groove back in here is 6.8 inches deep from the end of the part. And I modeled this such that I can actually, if I select the push rod piece, if you want to call it that, I can actually move the gauge the way it does, because I've constrained the parts so that I can do this. You can see how the gauge functions. There's a angle in there. And the slide is a mini, it's kind of like a miniature ball, or it's not ball, they're cross rollers actually. I was surprised when I looked at it carefully. This slide piece has a cross rollers in it, not ball bearings. And it's very small. It's only like let's measure the width of it. This is a model that I downloaded from a McMaster car. It's 560 thousandths wide, and the actual slideway itself is 1/4 inch wide. This little ball bearing that I've got that riding in the slot is 3/16 of an inch in diameter, and these are this shafting is 1/4 inch in diameter, and these red pieces that appear in the CAD are actually linear ball bearings. So the whole thing rides on ball slide and bearings to keep the friction as low as possible. So here again, if I move the actual push rod piece, and what's actually restricting the travel is this slot for the handle here. The slide could travel 1/2 inch, but I'm restricting it to about 360 thousandths of travel. All right, let's take the thing apart and look and see how this actually works. Pull the dial indicator out of here first. Now this could be any dial indicator. I've taken the tip off of it because of the way I didn't allow enough space for the tip of that particular indicator. But actually, I could use pretty much any dial indicator in there that would work. In fact, if I wanted more resolution, I could use something like this. This is a 1/10 of a 1,000th indicator. This usually goes in a dial bore gauge here, and if I was using this like a dial bore gauge, I could do that. It doesn't have enough travel to be used as like a groove measuring device, because this thing only has like 30 thousandths of travel in this particular gauge. I think I've got another one in here that's got somewhere. Yeah, this one. This measures in half thousandths, and it has a little more travel, like maybe a 200 thousandths or almost a quarter of an inch. So you could put any kind of dial indicator you want in this thing, really, that would fit in there. I've looked one up on a Mitutoyo website that's got a 1/2 inch travel, but it reads in 1/10 of thousandths like this indicator does. That's the one I'm tempted to get. Although for the particular application that I'm doing at the moment, I don't need that kind of precision, really. And let's see if I can get this thing apart here. It's a little bit tight sometimes. Okay. So I didn't show the machining of this part here in the video, but it's more or less the same as this one. It just has counterbores for the screws, and it's shaped a little bit different on this end. But I didn't see the need to show all that in the video. So I put a spring in here to kind of give me a little more, see if I can hold these things down. Let me put something underneath here because the screw is hitting on the table there. So you can see this little spring adds a little bit more force because the dial indicator all by itself doesn't quite have enough force to move everything properly. But this is a very light spring. I don't know, I got these at the hardware store, and so that's the way that ended up. So this can all be just lifted out of here, really, like this. The linear ball bearings just sit in there in these troughs, and then it's held together by that. Now the slide, you probably can't see it. You'd have to have some magnification, but actually this little slide is just a standard part from a McMaster car. They actually make smaller ones than this, but this is the smallest one they made with a heavier load rating, if that means anything. And it actually, like I said in the video, doesn't have ball bearings. It has cross rollers in it. There's like 5 on each side, and it's supposed to have like a I don't know, 30, I think it said 30-pound rating on weight, whatever that means. I'm not sure totally. And these I want to also say that these carbide anvils that I showed grinding, I took a little diamond hone and I kind of polished and honed them a little bit, and then ran it on the Scotch-Brite wheel on the grinder just to kind of polish and round off the sharp edges. Otherwise you'd have sharp edges digging into your part with those carbide tips like that. But you could put anything. This is actually a 3/16 diameter just carbide blank, used essentially to grind an end mill from, and anything that's 3/16 diameter would fit in here, and you could extend these out to whatever length needed to measure and shape the ends of it however you want. Now I shaped these, I don't know if you can see that with this camera, but these are 25 thousandths thick here, if I can measure it this way. And so that'll easily fit in my groove that's 40 thousandths wide, and I'll have a little bit of room, particularly at the radius of the insert. There might be a little radius on the insert, and so I want to be in the groove part of it. Although this groove actually isn't super close tolerance even, but it's just hard to measure back in there. And so this is the way it moves. And as you saw me in the video machining this part, there's an angled slot in there that's at 45 degrees, and the bearing, and it fits the bearing nicely, and the bearing moves it back and forth on the slide. And there's actually very little backlash in the whole mechanism. I guess either I got lucky or it just everything fit kind of nicely, but in reality the backlash will be taken up by the spring pressure here, so it's not really that critical. And this little linear slide is, like I said, really stiff. It doesn't move around. It doesn't have any play at all. So that worked out really good. And the thing has really nice feel to it. So that's what it looks like inside. I just took my hand grinder thing and put an abrasive disc on it, and just put this thing in my hand drill and just ground a groove deep enough for this snap ring to fit in here. It's just a regular, one of these, I don't know if you can see that, but it's one of these just snap rings. I bought that at my local hardware store as well. But all these parts could come from McMaster car. I bought the bearings and the slide, and actually I think some of the screws from McMaster car, and the little ball bearing here as well. You see me in the video using tweezers to hold that thing to try it on this shaft when I machined the shaft, because I didn't want to drop that thing in the chip pan. I'd never find it if I did that. I'd be kind of careful. And also, you noticed in the video, I don't know if you could see it here, probably not, but you can, after I machined away the ends and this notch or you know, flat in here with the little shaft to hold the bearing, you can actually see the thickness of the case hardening on this shaft, because this is that linear guide shafting material and it's hard on the outside. It's case hardened. I'm not sure what kind of steel it's made out of. It's I didn't really look at it. It's just the regular steel shafting. So anyway, that's what it looks like inside. Pretty simple. I only had to actually make this part and the shaft and this part and the anvil. The rest of it I just bought at the hardware store and from McMaster Car. So it's not really a very complicated thing to build. You could build one quite easily. One thing I did miss a little bit on the model, and I didn't notice it, is I had to cut a notch in here because the shaft here was hitting it when it came all the way forward. So that's my version of my dial groove gauge. It'll come in handy because I've run into this problem before where you can't measure a shallow, either a shallow counterbore up into something, and this will be really handy for that, or like this is going to be used for the first time for a small width groove, like the snap ring groove or something. So anyway, that's going to be it for this video, and I was my last video was on the first end of these 17.4 parts, but there was an issue with the material and I had to stop on that. I wanted to show the other end of it, which, like I say, this gauge is going to actually be used for on that end of it. So you could put this dial indicator in, and it would and you could get more precision that way, or you know, more resolution, I should say, maybe not more precision necessarily. I cut this a little bit thinner on one side down here so that when I tighten these screws it would clamp the indicator more securely, because it wasn't clamping it quite tight enough. So I took a few thousandths off of that one of the faces, I don't remember which one, on one of these parts, and that more or less solved that issue. So like I said, that's it for this video, and I hope this was of some interest to somebody, and maybe give you some ideas if you need to make some gauges yourself on how to maybe do it. So thanks for watching.